Hey gang, welcome to Computer Graphics. Today we're going to be continuing our discussions about lighting and illumination and reflection, and we're going to begin talking about, after we cover the basics of color and illumination, we'll move on and start talking about, okay, how do we model these things in computer graphics? So we're continuing our exploration of color and illumination and reflectivity, and then we're going to be moving into how do we do these things, how do we model these things in computer graphics. So let's pick up where we left off last time. Last time we were talking about the fact that about our anatomy of the human visual system, and we talked about the fact that we have rods which detect light and dark, and cones which detect color, where we have three types of cones. They're commonly called red, green, and blue cones, but a better, more accurate way of describing them are S cones for cones that are most sensitive to short wavelengths, L, which are cones that are more sensitive to long wavelengths, and then M, which are cones that are more sensitive to wavelengths of light in the middle. And so the short cones are what we normally call blue, the medium cones are what we normally call green, and the long wavelength cones are what we normally call red cones. So you can really only sense three different types of color, or more specifically, you can sense three different. You have three sensors that are most sensitive to a different wavelength. So you've got cones that are sensitive to short wavelengths, you've got cones that are sensitive to medium wavelengths, and you've got cones that are sensitive to long wavelengths. And your brain integrates all of that into the concept of color. And last time I was trying to argue that there is no unique, unambiguous colors in the real world. And we were just ready to get to an example. So take yellow light. Okay, well, you don't have a sensor for yellow light. You have sensors for red, for green, and for blue. And so what is yellow? Well, yellow, if you look at its hex code, the hex code for yellow is FFFF00. And we introduced these hex codes at the end of class last time. Basically, the first two digits is the intensity in red, the second two digits are the intensity in green, and the last three are in blue. So if you know that, and also it's in hexadecimal, so FF is 255, right? This is saying that red is at level 255, and that green is at level 255, and that blue is at level 0. Well, that means I've got some bright red light and some bright green light coming into my eyes, and I see that, my brain sees that as yellow. Even though there is no, if you define yellow light as light at a particular wavelength, there is no, quote, yellow, in quote, light. There is no light at that specific wavelength. But because you only have three sensors in your eye, three color sensors, we can stimulate those color sensors in a particular way to make your brain generate any color sensation that it could normally get by looking at the real world. And this is all very important because it's the basis of our monitor technology. So if you look at a light emitting diode monitor, an LED monitor, and looked at a pixel, well, we're looking at a screen here, and you see a lot of white and you see a lot of black. But really, if you were to sneeze on your monitor, or more sanitarily, flick some water at your monitor so that the little water droplets would act as lenses, you would actually see that a white pixel is not a white pixel. It's a red, a green, and a blue pixel. So it's a red, a green, and a blue subpixel that are so close together that when they're all shining at the same intensity, your brain puts those together and says, oh, that's white light. Because how does your brain perceive white light? It perceives white light because your red, green, and blue sensors are all doing a happy dance as as happy dance as they possibly can. So they're all three excited. That's how you see white. So that's monitor technology, and I wanted to take a little bit of time to talk about the idea of colors and computer monitors, and kind of look back in time and see if we can see the genesis of this idea. In the 1800s, people were very interested in color and in color theory, and there was one particular painter, George Seurat. He lived in the mid to late 1800s, and he was a French painter. And the interesting thing about Seurat is he was interested in not just in the artistic side of painting. He was also fascinated by what the scientists were finding out about the way the human eye worked and what color was and how the human visual system perceived color. So he developed had a theory, and from that theory he developed a style of painting that was called pointillism. And so basically he had the idea of creating images by putting lots and lots of little dots next to each other. And he also had the idea that, well, if the dots are close enough together, I can use a small number of colors, and the human eye will blend those together to create colors that aren't actually there. And if this sounds familiar to how I've described an LED monitor, essentially, 100 years before that technology had been invented, you had a French impressionist painter who was playing around with the very ideas and proving them in the area of art that 100 years later became the basis of our monitor technology. Now he called I said putting the little dots of paint was called pointillism. Now I have a hard time saying this, but his idea about the blending of colors, where you use a small limited number of colors and put dots close to each other, and your eye would blend them together. He called that chronoluminarism or chromoluminarism. Like I said, I have a hard time saying that, but he demonstrated it on a painting called A Sunday on the Island of La Grande Jatte, which he painted between 1884 and 1886. And here's what that looks like. And again, I'm showing it to you, over Zoom, and so you're kind of it's weird because I'm showing you through 21st century technology, right? An 18th century painting that was designed to demonstrate the fact that a limited number of colors, so that your eye could blend them together to form any color, and you are looking at it on a display that uses that technology with red, green, and blue. So there's like so many meta levels here going on that can make your eye and your brain hurt. But the idea is that if you got a really close up, the green grass is not really green. It's dots, right, of different colors. And the purple skirt, there's no purple in there, right? It's like blues and reds that your eye is blending together. And I have never seen this painting in person. I went to the Louvre right, in France a few years ago, and I was all excited because I'm like, well, surely this is one of the most, for geeks at least, Seurat is the most famous French painter, and I'm saying, well, the Louvre will clearly have tons of his work. So I used the little app, you know, to find where things are in the Louvre, right? And they had like one or two little sketches that he had made, and it turns out that almost all of the of Seurat's artwork is at, yep, Blake gave it away. It's in in Chicago, in the big in the big art museum in Chicago. So I went halfway around the world, or at least a quarter of the way around the world, hoping to see Seurat, and I was bitterly disappointed to find out that most of his work was far closer to home than I thought about. And Eric, thanks for throwing that link up there to a close-up of Seurat's work. And when you look at it, you will see it's just dots, and there are a limited number of colors. Now, he didn't use red, green, and blue. He used various colors, but I think he used, I want to say it was like he limited himself, I want to say to 4 colors. I could be wrong there, but I think it was like 4 colors. But I have a copy of Sunday on the Island of Bogorajat in my living room because I am a geek, and I don't put a lot of artwork or anything like that on my walls. My mom was one of these people who had lots and lots of knickknacks and stuff all over the walls, and she collected little music boxes and lots of stuff. And so I'm exactly the opposite. I no clutter, right? So my walls are pretty much bare. But I made a few exceptions. In my living room, I have a copy of Seurat's painting there, and in my guest bedroom, well, when I have it set up right, I have a photo taken on the surface of Mars. So I figured this says about all you need to know about Mike. Okay. All right. So we've talked about displays, full color displays being red, green, and blue, and that's really all you can see. And the next thing I wanted to spend just a minute talking about was, what would the world look like if we were a bee or a bird? Okay, this chart here shows where our S, M, and L cones peak at. And again, different sources will have these a little bit differently. Our red cones are shown to peak more towards green-yellow than in red. And other sources will show this shifted a little bit in this direction. But the idea is still that you've got 3 of these things. And another thing that's very true about the human visual system is they're not equally spaced. So our green and red cones are actually pretty close to each other, where our blue cone is fairly far away. So we don't have the separation that, I mean, it would be best if these were equally spaced, right? Because then you would have the most, you would be able to interpolate the colors more accurately. So the human visual system's kind of crunk. It's sort of crunk because it evolved a couple of times. Primates evolved color vision, and then they lost it, and then they re-evolved it. And so we're kind of, and when we re-evolved it, we didn't re-evolve it in the best way. Birds actually have the best system, and I mean, I can't show you how the world looks to a bird, but I can look at this graph and I can say birds have much better color vision than humans do. Why? Well, they've got 4 sensors rather than 3 sensors, and their sensors are far more equally spaced. So their color resolution should be far better than ours. Now, what does that mean? Well, clearly, if you look at like yellow, right, a color that none of us really have. Well, I guess the B is actually closer. None of us really have a receptor at the wavelength of yellow, right? But the inputs to the bird visual system, the inputs to the avian visual system are better for detecting yellow. You might say, but there's a trough here. Well, because yellow is actually going to falls right in the middle and is going to cause these two things to generate signals that are approximately equal. While with us, you know, yellow is the L. You're not getting a whole lot of input from your M cones, you know, and you are getting a lot of input from your L cones. So, but anyway, because these are more equally spread out, birds are going to be able to do a better interpolation. And also, you notice this fourth cone here, it's down in the ultraviolet. So clearly, there are colors. Birds can see colors between blue and ultraviolet that we totally can't see at all. In other words, they even if you discount color, they can see down here in the ultraviolet, and we can't see down here in the ultraviolet. Because they not only have rods that can detect at that range, they have cones, they can clearly see a wide variety of colors down in here that we can't. If birds see color, and I assume that in their brains they have a system like we do for making sense of the inputs of these systems. Bees are another thing. They can see well into the infrared, even further than birds can see. And they have three cones. They're more equally spaced out, so they probably have better resolution in some ways, although it's probable, because this drops off so far, that bees can probably barely see red. So Andrew is talking about mantis shrimp that have more types of cones, but they're in a more narrow band. So that's interesting too. So again, all of this just goes to reinforce what I started the lecture with on Monday, is that color is in your head. It's not a complete real world thing. Now, I said that I couldn't show you what the world looks like to a bird, but maybe the closest thing I can do is show you an image from an early color film, Ben-Hur, not the Ben-Hur from the 1950s before you were born and I was born, but the Ben-Hur from the 1920s, which was before you were born and I were born, and I think my mom was born. So, yeah, before my mom was born. My mom was born in the late 20s. And so Ben-Hur is a black and white movie. It's available on the internet. You should look it up and fast forward through it just a little bit. It's mainly in black and white, but there are some scenes that are in color. But this was one of the early experiments with color. That image that you're looking at there is red-green color. So essentially, there's only two colors that are in those images. There's no blue channel, and there's no blue channel, and that's why you can see that the image is in color, but you can also see that there are a lot of colors that are missing. You can clearly see her dress is red, and this is a greenish looking color here. This color could have been blue. Her dress might actually have been blue here rather than green. But because this is two colors and this image is red green, you see it's in color, but there are parts of the spectrum that are missing. This system of red-green color was actually used even up into the 1950s. You can find some inexpensive sci-fi movies from the 1950s that when most cheap sci-fi movies were in black and white, there were some that were filmed in this two-color process, the red-green process, to make it color. And if you choose your palette of clothes and stuff like that properly, you could get something that's not too noticeable. I mean, you'll notice at a subconscious level that things look a little weird, but if you ask someone what's wrong, they might not be able to say it. So, for example, if you shoot out of doors, you know, you'll see that the trees are green, but the sky will be gray. All right, the gray is actually kind of close to blue, so it's okay. Now, if any of you have ever played around with an art class, you might be saying, Mike, you've been saying that red, green, and blue are the primary colors for the last day and a half, or the last lecture and a half. And I learned something totally different in my art class. I learned that the primary colors were cyan, which is this color here, magenta, which is this color here, and yellow. And that's called the cyan, magenta, yellow system, or the CMY system. And you might say, wait, you're throwing me for a loop here. I don't understand. Well, when you mix light, L-I-G-H-T, the primaries are red, green, and blue, okay? But when you mix pigment, you know, colors that you can, like, you know, make into paint, the primary colors are cyan, magenta, and yellow. And you might say, I don't understand this. You just told me all about the visual system and our red, green, blue. Yeah, that's true. But color, the color system is, for light, is what we call an additive system. The color system, so RGB is an additive system. If I want to get yellow light, I add red light and I add green light, and those two lights together show me yellow. So when you're looking at this on your screen right now, that color is being produced by pixels that are generating red light and green light, and they're generating those lights so close together that your brain is blending them and seeing yellow, okay? But if we were talking about pigment, so pretend for a moment that you're not looking at this on a display, that you were looking at this printed on a page. Well, then even though you'd be seeing the same colors, they'd be being generated differently. So how does the CMY system work? Well, the system for pigments is subtractive. Okay, so this color cyan here, cyan pigment appears to be a bluish green. And it appears to be bluish green because it absorbs, it subtracts red, and thus it reflects blue and green. So cyan subtracts off red, okay? Yellow pigment is a combination of red and green. It subtracts off blue, and magenta subtracts off green. So if I take a pigment, if you look here, this is in the middle, it's black. Why is it black? Well, because the cyan is subtracting red, the magenta is subtracting green, and the yellow is subtracting blue. Well, if you subtract red, green, and blue, what do you end up with? Black, right? The absence of reflected light, because if you mix all three of the pigments together, you're absorbing, you're not reflecting any of the colors, you're absorbing all of them. But what happens if you mix cyan and yellow together? Well, again, cyan is subtracting red and yellow is subtracting blue. So if you subtract red and blue, what do you see? What do you get? You get green. Okay, and it works the same way. I mean, if I were to take cyan and magenta, right? The cyan is subtracting red, and the magenta is subtracting green. So if I mix them together, I get blue because it's the only thing not being subtracted. So the system that artists use, that was what I should have asked Jerry rather than asking him what color is. I should have said, Jerry, what are the three primary colors? Next time, next year, when he comes in to give his little spiel, I'll ask it to him that way. And that way students will be completely confused at the first part of my lecture when he says, well, it's cyan, magenta, and yellow. Everybody knows that. And for an artist, he would be right, because artists deal with pigments. So anyway, although he's in video games, so he knows about red, green, and blue. But if you took a classical artist who never gave a frack about computers, they would be talking to you about the CMY system. Okay, so that's color. I think color is totally fascinating, but let's move on to more computer sciencey type things. So now we know a little bit about color. We know that humans can basically only sense red, green, and blue, but we can jiggle those to generate any kind of color. So we've talked a little bit about light. So what we want to develop is what's called an illumination model. Now, an illumination model, as I define here in the first sentence, is a mathematical model of the interaction of light with a surface. That's what an illumination model is. It's a mathematical model for the interaction of light with the surface. Now, our models in computer graphics are empirical. The word empirical means developed by observation and experimentation. Another way of saying that something is empirical is to say, well, it works because it works. I jiggled a bunch of things and I came out with some formulas and I programmed them, and hey, the results were pretty good. So this is what we went with. Scientists like physicists stare down their nose at empirical models. They're the low-class proletarian models, because the physicists would prefer something that has some kind of a formal theory behind it, right? And that is based on more on first principles, rather than something that just, oh, it's empirical. I fiddled around with it and I got it to work. So that's what the word empirical means. It means developed by observation, experimentation. I tinkered until I got something that worked pretty good. Don't ask me why it works. I don't have a theory for why it works necessarily, but it works. Now, with our illumination models, we can because we do know, humans do know quite a bit about light and physics. We can kind of say, well, here's where the model cheats. The physics would do this, but the model does that. And so we can explain the parts of the model and why they work in terms of light, and so you can see just how much the model is cheating. Now you might say, but Mike, if we know the physics of how light works, well, why do we come up with these illumination models that you just said cheat? Well, because remember, in computer graphics, everything is about speed, speed, speed. Eric wants, though he doesn't really need, those 144 frames a second, right? That will make him feel good as it was you, Eric, wasn't it? That will make him feel good as he plays his video game and convince him that everything looks much more smooth because he's rendering 144 frames a second. Yeah, it's necessary. Fight me. Yeah, well, that ought to be bite me, but it's good. Anyway, we can meet in the middle and say that while Eric should be spending those compute cycles on more detailed models of his characters, he would rather spend them on frames per second. But to get either of them, we have to have an efficient lighting system, an efficient illumination modeling system. So it's necessary to cheat because we can't afford, it's like, okay, you really want prime rib, but you're going to sell for hamburger because It's still beef, and at least you can afford the hamburger. Okay, so our models of light will model I guess you could say two types of light sources. We will model light emitting sources, and by their name you can see that they're things that give off their own light. And we will model light reflecting sources. Those are non-emitters that reflect light. And really, you look around you, and almost everything is a light reflecting source. I look around me, I see a computer, I see the computer screen is an emitter. I look at a table, you know, I look at my walls, I look at my ceiling, and most everything in my house is a reflector. And the only reason why I can see the table here is because it's reflecting light. If it didn't reflect light, I wouldn't be able to see it. Well, it'd be black, right? And if everything were black, well, you're in the dark and you're stumbling around and bumping your knee. So light emitters and light reflectors. Now in the real world, honestly, in the real world, everything is a distributed light source. And by that I mean that the light originates from some surface, whether that surface is the fluorescent light bulb or whether that surface is an LED. In the real world, there's no such thing as a point. All right, a point is an infinitesimal mathematical position in space. There are no points in the real world. But in our computer model, all of our light emitting sources, at least in this class, all of our light emitting sources will be point light sources. Just because they're easier to model. If you want a distributed light source and all your modeling is point light sources, you can put a whole bunch of point light sources fairly close to each other, and that can simulate a distributed light source. However, it gets extremely expensive. Each light source adds for calculations. So you can't really say, oh, I'm going to model this fluorescent light by 1,000 point lights. Well, you can do that, and then you can revel in how many seconds per frame you're getting. So our light emitting sources are going to be modeled as point light sources. We have light emitters and we have light reflectors. So then we need to start talking about what kind of reflections we get. There's one kind of reflection. It's called diffuse reflection. But we're going to start by defining what ambient light is. Ambient light is kind of like, if you think about physics, it's kind of like air pressure. Okay? We all know what air pressure is, you know, and you learned in physics, PV equals nRT or whatever the friggin' thing is, right? Pressure, volume, you know, is proportional to temperature. So you raise the temperature and you keep the volume the same, the pressure is going to go up, etc. The ideal gas law, I think that's called. Even though I studied that 40 years ago, for some reason it pops back in my head. But ambient light's kind of the same thing, in that ambient light is light that is coming from all directions in the environment, hitting objects and being reflected equally in all directions. It's background light. Okay, it's the level of light in the environment that is just sort of the general background level of light. Now, why do I say that it's like the pressure law? Well, actually, when you get into the physics, your prof will start saying, well, you know, in aggregate, the gas molecules are acting as PV equals nRT, but in reality, we know that actually the individual gas molecules are just bouncing around randomly, and when you add more energy into the equation, raise the temperature, they move more vigorously. and the fact that they're hitting the walls harder because they're moving faster and more vigorously, in aggregate, we call that pressure, right? So the physicists don't actually model the pathway of every individual molecule of gas. You could if you had enough compute resources, but it would be stupid to do that because in the end, it would kind of come out to a constant that you get from the very simple formula PV equals nRT. Same thing with ambient lighting. Light rays, are rays. They hit surfaces, they bounce off in particular directions. They come from directions, they bounce around. So you could model, all of those rays of light and how they bounce around in the environment. And you will find that a large percentage of the rays are coming in from pretty much every direction and are bouncing off pretty much in every direction randomly. And so we won't need to calculate all those angles and all those light rays and do all of those tremendous calculations. We will just treat it in aggregate. Okay? So that's ambient light. And now, clearly, when you start talking about lighting, there's more than just ambient background light in an environment. There's also the light emitting sources. And so really, when I look in my living room or my kitchen, where I'm actually sitting right now, there's a general level of background light. Well, some of that you can't see because I have the Geiger alien drawing there. That's the alien, right, from the first Alien movie. But behind me, I have a fluorescent light in the kitchen, and in front of me, I'm looking out my kitchen onto my back porch and backyard, and the blinds are open at an angle, so I'm getting some light coming in from outside. And right above me, you can see my shiny semi-bald head. That's being illuminated, not eliminated, thank God. It's being illuminated by the lights above my kitchen table. So some of that light, like on this side here, you can see just how bright and white Mike is, right? But if you look here under my droopy chin, it looks darker. Well, that's because if we modeled my kitchen light as a point light source, which we could, that point light source is hitting the top of my head, right? But my chinny chin or under my chin is darker because really it's not being directly illuminated by any particular light source. That's just the overall general level of lighting in the environment of my kitchen. Okay, so my face is being illuminated by a combination of direct illumination from light sources that we would model as point light sources and from overall background light. If I turned off my kitchen light, okay, Google, turn off the kitchen light. Voila. Right, but it's interesting because of technology now. What did my camera do? My camera adjusted the brightness automatically. So while my face went darker for a while, it lightened back up again. But that was due to our wonderful 21st century technology here. So anyway, that was funny. Okay, okay, Google, turn my kitchen lights back on. Okay, so in addition to illumination, now a lot of times you'll hear me say illumination, and sometimes you'll hear me say reflection, and sometimes I'll say an illumination model, and sometimes I'll say an illumination reflection model. Technically, specifically, when I say illumination, I'm talking about light coming in and hitting a surface, modeling how that light arrives at a surface, how much light arrives at the surface. If I say reflection, I'm talking about the light that bounces off of the surface. So we have an illumination reflection model is, or sometimes I just shorten it and say an illumination model, but it's really both. It's computing how much light arrives at an object, but what we're really interested in is how much is reflected. So really sometimes people just call it a reflection model because it is generated. You wouldn't see it without the level of intensity that's generated and at that point or reflected at that point. So that's why we call it a reflection model. So we have in the quote standard lighting model that everybody uses, we have 3 different types of reflections. We have what's called ambient reflection, or more formally, ambient diffuse reflection. We have emitted diffuse reflection of point light sources, which oftentimes we just call this diffuse. Now you might say, wait a second, Mike, this is ambient diffuse and this is emitted diffuse. Why does this one get to be called diffuse? Well, it does. And if you say ambient light, again, is light that's coming in from all directions and is bouncing in all directions. When I say ambient diffuse, I'm really saying environmental light that bounces off in all directions. So the diffuse here is talking about the way the arriving light is reflected. So ambient is light that's coming in all directions and being reflected in all directions. There's no such thing as ambient non-diffuse reflection. That doesn't exist. That's why most people just shorten this and say ambient reflection. Because if the light is coming in from all angles, clearly it's going to be bouncing off in all angles. And so again, this is often just called ambient reflection. But I wanted to throw the word diffuse in there because diffuse means that the light rays go out in all directions. So again, ambient diffuse reflection is often just shortened to ambient. Emitted diffuse reflection of point light sources. Well, this is a mouthful, so again, we frequently just say diffuse, right? Even though, again, ambient is also a type of diffuse reflection. But emitted diffuse reflection, this is saying that you've got light coming in from a point source, okay? It's emitted by a point source, but it's reflected in all directions equally. So basically, emitted diffuse reflection is whatever light gets to some point on an object from a light source, a point light source, once it hits, that light will be reflected in all directions. And that's going to mean that what you see doesn't depend on the angle between the viewer and the surface, because it doesn't matter where the viewer is, the light gets reflected equally in all directions. So with any kind of diffuse reflection, you don't have to model where the user is, where the viewer is, because light is reflected equally in all directions, so it doesn't matter where the viewer is. The last type of reflection that these models capture is what's called specular reflection. Specular reflection is light that arrives at a surface from a particular direction and is preferentially reflected in a particular direction. Specular reflection is what generates highlights on an object. So if you're looking at like a shiny brass metal bar, right, there will be points on it that catch the light and glint the light, a very bright highlight. That's what specular reflection generates. But those highlights are only depend on where the viewer is and where the light source is. So computing specular reflection is way more expensive than ambient or diffuse because you have to take into account where the viewer is. And in fact, these things are on a spectrum. Ambient diffuse reflection is easy to compute because there's no angles involved. You don't worry, there's no one light source, so you don't have a lighting vector, and the light goes out in all directions, so you don't have to worry about a view vector. Emitted diffuse reflection, as we'll see here in a minute, you don't have to worry about where the viewer is, but you will have to keep up with where the light source is relative to the surface you're modeling. So diffuse reflection of point light source, you'll have to keep up with the surface normal, and you'll have to keep up with the lighting vector. Specular reflection, you have to keep up with the surface normal and the lighting vector and the view vector. So it's more complicated, but it looks nice. So what does all this mean? We will be combining these things together using this general formula. And what we'll be doing with the rest of today's lecture and Friday's lecture is we will be building this thing out, okay, the details of it. But here's the overall picture of it. The intensity of light is equal to the ambient light in the environment plus the diffuse and specular components. So you might say, what is this sigma and what are these? Think about this. I was just describing my kitchen, and I was saying, well, there's fluorescent light on the ceiling in the kitchen behind me, and there's these lights over my kitchen table, and also the shades are open, so there's light coming in from the outside. That's at least 3 different light sources there. If we modeled each of them as a point light source. So each of these light sources have to be computed separately. So this is simply saying here, I goes from 1 to n. This is there are n light sources in my environment. So the overall intensity is the amount of background ambient light in the environment, plus let's say there are 3 light sources, the amount of diffuse light that I'm getting from the first source, the specular light from that first source, the diffuse light from the second source, plus the specular light from the second source, plus the diffuse light from the third source, and the specular light from the third source. All of that together gives us our total intensity of light for 1 pixel on our screen that represents 1 point on 1 polygon. Beginning to see why this is going to be more expensive than what we've been doing, and why we have to cheat, because even with cheating, we're going to be doing a whole mess of computations. Now, really, you have to do 3 times as much work if you want to render a scene in full color. So the bad news is you have to do 3 times as much work to do color. The good news is you only have to do 3 times as much work. You don't have to do, because human beings are blind except for red, green, and blue colors, you only need to worry about the intensity of red, the intensity of green, and the intensity of blue. These equations are just a copy of this equation with a little subscript red behind every color source in the red, and then green, and then blue, because you can get a full color if you treat each of the 3 color channels, red, green, and blue, separately. So the bad news is you got to repeat it 3 times if you want to do color and keep up with red, green, and blue separately. But the good news is you're getting an infinite number of colors, essentially an infinite number of colors, millions of colors for free, because you only see those infinite colors by combinations of red, green, and blue. And I say infinite in 8-bit RGB color, which is 24 bits total, 8 bits for red, green, and blue. In those 24 bits, you have like 24 million colors, something like that. And we've settled on that because humans can't distinguish color any more than that. Eric probably doesn't want 8-bit color or 24-bit color. Do you, Eric? How many colors is it going to take to make you happy, Eric? Let me look over in text here and see. Or are you color agnostic when it comes to your games? Maybe you don't care about color like you do about frame rate. Eric is being very quiet in chat. Maybe he went and made himself a sandwich. 2-bit. I love you guys. Thank you, Noah. You made my day. 2-bit colors with 140 seconds. You guys. Okay. So what does this it would look the same as your 144 frames a second look to 60 frames a second, Eric, which is you wouldn't notice any difference. If you want to spend more money, there are some systems that use more bits per pixel of color, but really pretty much 8 bits for red, 8 bits for green, and 8 bits for blue have been around since that's been the standard since I was your age, right? And most standards have changed, but that one hasn't because it's good enough. We reached the limits of what humans could see. Okay. So what does all this look like? I've given you the equations, but what does it look like? Here's a sphere, right? And it's a red sphere that is lit by one point light source. And they're mapping out here the various parts of the color. The highlight would be generated by the specular part of the equation. The diffuse reflection here is light that's coming in from a particular light source, so it's brighter here because more light's hitting the sphere from the light source, say, than over here. This is not, it's on the back side of the sphere, so according to the light source, so it's not being illuminated directly by the light source. But so this is light that's still coming in a particular direction, but it's being reflected equally in all directions. And then this dark part over here, it's not black, it's dark red. That's the ambient component. So you can see the specular, diffuse, and ambient. If you're constrained in compute resources, the first thing that people throw out is the specular component. You don't get the pretty highlights, but you can save yourself a lot in computation to do that. Okay. Does that make sense? All joking in the chat room aside, do you see what I'm saying here? So, summarizing, we've got a model for the intensity, the reflected intensity of a point that we're illuminating. To get the intensity, the color of that pixel, well, if you're here, we're not talking about RGB, so it's not really color, but to get the grayscale intensity of the pixel, you have to combine the background ambient lighting and the diffuse and specular from every light source. Now, and if you want it in color, you're going to do it in RGB. Now, we're going to cheat. This guy here is cheating in the way that we're going to cheat in this class on your programming assignment to make things somewhat practical. He or she is using one point light source. So the summation goes away and we get back to the first equation that I gave here, all right? So there's only one, no, it's not the first equation because I have the summation here. It would just be ambient plus diffuse plus specular. But the second thing is even though you go, oh, this is a red ball, you don't have to, you only need one equation, right? You only need the intensity equation, which you map to the red channel, and you leave off blue and green, you set those to 0. So even though this is red, it's not, you don't need 3 copies of the equation for red, green, and blue to compute that. You just need one version of the equation, and all you do is you take that intensity and you map it into the red channel. Okay. All right. We're cooking with gas. So now then, like I said, over the rest of this lecture and next lecture, what we're going to be doing is we're going to be saying, okay, how do we compute ambient? How do we compute diffuse? How do we compute specular? You've got the framework, you've got the model, but I haven't explained how to compute these pieces. So let's start with the simplest piece. Let's start with ambient, all right? So we're going to compute ambient diffuse reflection. This picture says it all. Light rays are coming in from all different directions. They're hitting a point on a surface. That surface obviously has some surface normal associated with it, but we don't even need to worry about computing the surface normal because the light is reflected equally in all directions. So since the light is coming in from all directions and the light is going out in all directions, we don't need to worry about any of the vectors. We don't need to worry about the surface normal or the lighting vector or the view vector or the reflection vector. We don't have to worry about any vectors. So the computation becomes extremely simple. Here's the computation. Ambient light is equal to the intensity of the ambient light. That means the level of lighting in the environment times something we call K sub D. K sub D is the constant of diffuse reflectivity. KD is a feature, is an aspect, is a characteristic of the object we are modeling, whereas the IA is a characteristic of the environment that the object sits in. So IA is the intensity of ambient light, okay? It is the level of lighting that's around us. KD is the constant of diffuse reflectivity of an object. You need both of those things. Mike, why do you need both of those things? I am wearing what we call a black t-shirt, okay? Because I didn't feel like putting on a button down today. The color here and the color of my pasty white skin is very different. My physical body characteristics don't really influence the environmental light. That's not quite true because this is reflecting, right? And so since my white pasty face is reflecting, the light from my face hits the walls, and from the walls it hits the floor and the ceiling, and blah blah blah, and it comes back and helps illuminate my face. So yes, my face is reflecting light into the environment. So in a teeny tiny way, it's affecting the environmental lighting. But in general, we can think of the environmental lighting, the ambient lighting in the environment, as being independent from my I'm sorry, I'm getting a call coming in on my phone, which is bugging me. Let me see if I decline it. There. Okay. Are we all still here? Somebody say something to make sure I didn't lose audio.
Still here.
Yeah. Okay, good. So intensity, IA, is the intensity of ambient light in the environment. You multiply that times the diffuse reflectivity of the object you're rendering. You need both of those things because this color is different from this color, right? And so the constant of diffuse reflectivity is giving you the characteristics of different parts of me in this case. You need both of these things because, again, if I were to decrease the ambient lighting, these colors would change, right? If I were to eliminate all of the light, everything would be black. You wouldn't be able to see anything. No, I would be if there's no light for me to reflect, I'm reflecting nothing, right? So it's the interplay of the light in the environment with the characteristics of the object that give you the ambient reflectivity for a particular object. Does that make sense? So, it's just common sense. You need both the level of light and the characteristics of the object to say what the color of the object is going to look like. And I'm talking about intensity here, but the same thing applies to color, right? You might say, well, no, you said this is a black shirt. This is pasty white skin, kind of pinkish actually. But if you go to a club, right, where they have, the sort of the very, very violent black lights where a lot of the light is in the ultraviolet, then things look very different, right? Your white shirt becomes this blindingly bluish purple kind of look to it, and everything looks off, which I think is fun, which is why we do that in clubs sometimes. We like to play around with our senses in clubs, with the environment and the things that we consume. So if you were to think about the color of light, the color of the light in the environment actually affects the color that an object appears, even though it doesn't change the constant of diffuse reflectivity. That's an aspect of the object. The lighting can change. Like I've got multicolored lights over my fireplace, which you can't see, but right now I have them set to blue. I could ask Google to set them to green or to red or whatever. Now, to do ambient in full color, you need to talk about the ambient component in red, the ambient component in green, and the ambient component in blue, if you're doing a full color model. So, if we're, and this is what we're going to do as we talk about these things. We'll talk about the monochrome model, and I'll always try to remind you, but hey, remember, if you're doing full color, it's not just one intensity. You've got to do the intensity in red, green, and blue. But these are exactly the same equations. I just threw a color subscript on the end of everything to let you know that you would really have to do the equations 3 times. Does that make sense? A computational detail. What scale should we use for our colors? And generally, we try to set things up so that the ambient plus, if you've only got one light source, 1 point light source, the ambient plus the diffuse plus the specular add up to 1 under maximal illumination conditions. So we try to scale things so that the final ambient, so that the final intensity term, which remember is ambient plus diffuse plus specular, ends up being 1. So we try to scale things that way. So we tend to run things as fractions between 0 and 1, so that the range will end up being somewhere between 0 and 1 for the final intensity. And then kind of as a last step, we multiply that by 255 to get a color level. Because remember, most systems, every color, red, green, and blue, is somewhere on a scale from 0 to 255. And eventually, if we're going to send a pixel command to Python to tkinter, well, we'll do it through a line draw 1 pixel long, as you've already seen. But there's a color code there. That color code will need to be 200 hexadecimal code that indicates a red, green, and blue, each of those with up to 200, from 0 to 255. So eventually we have to scale that. But generally, while we're doing all of our computations, we keep everything between 0 and 1. As Andrew says, well, of course, we'll need to convert the colors we are using into hex to be able to do the maths. looking ahead, doing spoilers, Mike O'Neill is kind. You know, I have a heart somewhere. It's like the Grinch. Maybe it's 2 sizes too small or something, but I do have a heart, and we will cover. I created the code, and I'm going to give it to you for doing that conversion to red, green, and blue, because I'm a good dude. Okay. So here I talk about, like, you know, in the RGB illumination model, a scene containing a moderate amount of white light might have, you know, 25% ambient red, green, and blue, together with an object of a yellow object of medium intensity, might be KD of 0.5 in red, KD of 0.5 in green, KD blue of 0. So you see that this would be a yellow object in a moderately bright background illumination. So the background illumination is providing 25% of the light, and it's white light because all 3 components are set the same, and the object we're modeling here is yellow because only red and green are active, blues off, and they're each at 0.5. Okay, so if you multiplied these together, you would get this as the color code of this yellow, this dot on the surface of this yellow object would be 0.125 from the ambient component, and if you, after multiplying by 255, basically you have 20, I shouldn't say 20, 20 hex, 20 hex, 0 hex, right? Because this isn't 20, it's what, 36. Okay, or 32, 16 times 2, Mike. Okay. So next up, we have emitted diffuse reflection of point light. So now then, we've got a light source. Light's coming in from one direction. So before, remember, light was coming in from all directions. Well, now light is coming in from one direction, hitting the surface. But when it does, the light that gets to that surface gets reflected in all different directions. So you might say, well, that's fine. I move the thing, the direction changes, but it's not going to really change things in any way, is it, Mike? Well, actually it is. You're going to have to keep up with the surface normal and the lighting vector and the angle between them, phi in this case. By the way, the lighting vector is not the direction that light is coming into the scene. The lighting vector is the direction pointing towards the point light source. So the difference between the surface normal and the lighting vector gives you an angle, phi in this case, and that angle determines how much light actually reaches the surface. This is called Lambert's cosine law, and it's easy to see graphically. I like to think in terms of pictures. And so these pictures, because when you start giving me math, I start getting a little squirrely until I can see in my mind what that math actually means. So what we have here, we have three little diagrams, right? This is, and they're actually kind of, this is sideways. So turn your head sideways like this. And you see you've got a surface and you've got a surface normal. And all of the light rays are coming in directly overhead. So it's as if, going back to this one that's easier to see, it's as if the sun is directly overhead. So the light rays are coming in like this, which means the lighting vector is going out. So the light vector and the surface normal are identical. When the light is directly overhead, the light's coming down like this, the lighting vector points towards the light source like this. So the surface normal and the lighting vector are the same. And so in that case, 100% of the little light rays are hitting the surface. And once they hit the surface, remember, they're reflected equally in all directions. So we haven't changed anything. Whatever gets to the surface is going to go out in all directions. So what happens as we increase the angle? So the angle here is 0, right? Well, as we increase the angle, here I'm showing things at a 45-degree angle. Now, when I created this graphic, I was very careful to take this line that had a fixed length, right, and I rotated it so the length of this line is exactly the same as the length of this line here. I've just changed its orientation. Now, each of these little light rays I drew them very carefully to be parallel to one another, or as close as parallel as I could get, right? It's interesting. There are 10 light rays here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so when the angle is 0, all 10 of the light rays hit this little surface and bounce off. Here, if we look at an angle, all 10 of the light rays aren't going to hit the surface. 1, 2, 3, 4, 5, 6, 7 light rays hit the surface, and 3 of them miss it. Interestingly, the cosine of 45 degrees is 0.7, 07, blah, 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 but it's 0.7, right? And that's telling you that 70% of the light reaches the surface. As we continue to rotate this surface compared to the direction of light, well, what we find out is that the cosine of 90 degrees, that is when the surface normal and the lighting vector are separated by 90 degrees, the cosine of 90 degrees is 0. None of these light rays hit our infinitely thin plane. So the amount of this light source that hits the surface becomes 0. So in other words, you vary between all of the light hitting the surface, 100% or 1, 75% of the light hitting the surface when you're at a 45-degree angle, and 0% of the light hitting the surface when you're at a 90-degree angle. So the angle between the lighting vector and the surface normal will determine how much this surface is lit by this point light source. Okay, that's conceptually what's happening here. Next time, we'll get into the math of computing it, but that's the general idea. Tomorrow, we all have our code walkthroughs. I hope everybody is signed up for a code walkthrough at this point. If you haven't done that, please take a second to do that now. And then on Friday, we'll pick up the lecture here. I've already got the assignment written. I'll either give the assignment out on Friday or I'll give it out on Monday. There's still a lot of stuff for us to cover, but there's a 2-week time period to do the next assignment. And quite frankly, if you've gotten the current assignment working, and I hope all of you have, if you've gotten the current assignment working, the next one is not that bad because it builds straight off of what you guys have done in the current assignment. I'm going to go ahead and close things down because we're at the hour 15 mark. I will stick around to answer the couple of questions that I see in chat after I close things down. But anyway, gang, I will see each of you for our 15-minute meetings tomorrow, and then I'll see everybody again on Friday. Have a good day.